Good morning, everybody. I am Mehnaz. I'm a PhD scholar working with Professor Shashank Vishwari, and my PhD project is funded by University, in which our prime objective is to look into different types of claims and understand if we can develop the test methods that can be used at the industrial level to check the quality of calcination. So let's talk about the main outline of my presentation is I'm going to first talk about what are the different clay calcination technologies that are available both at the laboratory level as well as at the industrial level. Then I'm going to talk about the different test methods that we can use to assess the pozzolanic potential of the calcine clays. We can use advanced characterization technique. I'm going to talk about that. And also, we can also use simple test methods that are used for different supplementary cementitious. How we can use those test methods to the calcine clay system. I'm going to talk about that in my presentation. And finally, at the end, I'm going to also comment on what are the different factors which affects the pozzolanic reactivity of calcine clays. So when we talk about the application of the clays as a supplementary cementitious materials, we know that it involves various stages of processing. The first step that is involved is the geological survey. We need to identify what are the potential clay resources, and then we need to collect the samples from the mine. So Dr. Rashmi talked about this in detail, how we can start with the geological survey and then how to collect the different samples. While the second step, that is to carry out the different techniques and to determine the composition of the clay so that we can identify from a large number of samples that we have collected from a mine to identify what are the potential clay samples that we can use for the application LC3. Dr. Raki talked about this in detail, how we can use like PGA, XRD, XRF, and finally we can identify those clay samples and we can go ahead and produce limestone calcine clay cement. But once we have identified those clay samples, we need to calcine those clays and we need to assess the pozzolanic reactivity. So in my presentation, I'm going to talk about this third step, that is the calcination, and how to use different techniques and how to test the reactivity of these clays. So before I speak further about the calcination, let's have a quick recap what basically happens when we heat the clays. There are different chemical reactions that takes place when the clays are heated. For example, at very low temperature, around 100 to 200 degrees centigrade, the first process that happens is the dehydration. In dehydration, the water molecules which are absorbed on the surface of the clay, they are removed, or the water molecule which is present between the interlayer spaces in case of 2 to 1 clay minerals, they get removed. So just from dehydration process also, we can get a rough idea what type of clay mineral it is present. Because granitic clays show a very less dehydration phenomena, like the mass loss in a very high-grade granitic clay, it will be just around 1 to 2%. While for the cementite clay, these clays show a very pronounced dehydration. So it's a rough indication whether our clays have 1 to 1 or 2 to 1 type of clay. And that is what Rafi also pointed out. That's the reason now when we are drying the sample, we are drying the sample at 100 degrees centigrade so that we can see this dehydration phenomena. After that, the second process that can happen in the clays, depending on the composition, we might see a mass loss roughly around 300 degrees centigrade. This mass loss, it can be because of the goethite. If your sample contains gibbsite, then you might see mass loss in this temperature range also. Then when we further heat the clays, then you will see the dehydroxylation phenomena. So what happens in the dehydroxylation? Basically, the clays we know have a crystalline structure and the hydroxyl groups are connected to it. When we heat those clays, they basically get dehydroxylated. Those hydroxyl groups are removed and these crystalline clays, they transform into the amorphous. We call this process as the dehydroxylation. You can see in this diagram, there's a very broad range of this specified from 400 to 900 degrees centigrade. This is because we have found that the dehydroxylation temperature can vary significantly. It depends upon the composition of the clay. One of the factors that we have found that affects the dehydroxylation temperature range, first one is the type of the clay. In general, we have found that 1 to 1 type of clays dehydroxylate at a lower temperature in comparison to 2 to 1 type of clays. Other factor which we found that influences the dehydroxylation temperature, it was the degree of crystallinity. The clays which are highly ordered, they dehydroxylate at slightly higher temperature as compared to the clays which have a higher degree of disorder. And if we will calcine or heat the clays further, after the hydroxylation process, there is another phenomenon which is called as recrystallization. So in the recrystallization, there can be different crystalline rocks formed, like spinel can be formed, light or crystallite can be formed depending on what is the activation temperature. So it's important for us to understand how these different chemical reactions will have an influence on the pozzolanic reactivity. So when we are teaching the clay just about the dehydration phenomena, those clays will show very low pozzolanic reactivity because just by removing the dehydrated water that is absorbed, the clays are still in crystalline form and you will get a very low pozzolanic reactivity. It is only when we heat or calcine the clays just above the dehydroxylation temperature, we will get a high reactivity. Why this is happening is because the crystalline nature of the clay, it gets transformed into the amorphous phase, which has a very high specific surface area, and that form of the clay, it shows very high reactivity. But if we further increase the temperature, and for example, the clay has reached the recrystallization phenomena, in that clay the recrystallization phenomena has occurred, then again the pozzolanic reactivity decreases. So this highlights that there is an optimum calcination temperature for each clay in which we have to calcine so as to achieve a best performance in the cement blend. Now the question is how to identify this optimum calcination temperature. This is not straightforward. We cannot just assume the calcination temperature of 700 or 800 degree. It will not work for all the composition. We need to properly look into detail to identify what's the optimum calcination temperature. As a quick tool, I can say that you can check what's the optimum calcination temperature from the TGA curve. You can carefully look at what temperature the dehydroxylation process has completed, and you can just take a buffer of maybe 40 or 50 degrees centigrade. Because if you will increase the temperature further, there's a possibility of recrystallization. You can accurately predict it using the TGA technique. So to calcine the clay, there are different technologies that are available. First one is the soak calcination. There is flash calcination technique also available. Other than these two techniques, there are also some of the emerging calcination techniques that are available. Like fluidized bed is there. There's the solar calciner and the microwave calciner. So at the laboratory level, we calcine the clays using the laboratory muffin furnace. This process is called as the soak calcination. So what we do in this technique is we first take the sample, we place it in an alumina tray, and then we heat the sample at, for example, we heat the sample to a predefined temperature range what we have determined already, and then we maintain that temperature for a sufficiently long period of time. So this process is called as the soak calcination. So if you want to calcine the clays using the soak calcination method, the pre-treatment that we require is first we need to homogenize the sample, which is must. Then we need to do the crushing of the sample. We can crush the sample either in a jaw crusher or maybe simply using a hammer to reduce down the size of the particle. What we do in our lab, we check the particle size approximately between 2 to 10 mm. It seems to work very good. The most important thing that we have to be careful when we are calcining the clays in the laboratory chemical furnace is what is the thickness of the material that we are taking. We have found that we should keep the thickness of this material just up to 20 mm. Because we have found that when we are keeping the thickness higher than the 20 mm, what is happening is actually the top layer of the material may be fully calcined, but at the bottom layer, the material will not be able to achieve the same temperature, and that clay will be under calcined. Overall, your clay will not be properly calcined. So the thickness should be limited to 20 mm, and roughly we keep a residence time period of 2 hours, and we found that when we keep the residence period of 2 hours, we are able to achieve a uniform heating in our sample. Once the calcination is done, we need to do the grinding, and in the grinding, we have to follow the protocol that all the calcined clay samples, it should be finer than 25 micron C. But to calcine the clays, we can use this approach for calcining only smaller quantities of clays. To calcine the clays in a large quantity at an industrial level, we require rotary kiln, for example. In the rotary kiln, what we do is first we place the roller to feed on one side of the shaft, and then on the other side of the shaft, you can see we fire the clays. In the first zone, you can see there is a dehydration process which takes place, because in that the temperature is not very high, and in the second shaft the temperature is very high and the dehydroxylation process takes place. The clay lose their attached hydroxyl group and they transform into the amorphous material. The key important thing here is that if we, for example, want to calcine our clays at 800 degrees centigrade, let us assume, then we have to keep a flame temperature 100 to 150 degree higher. If for example, we want to calcine at 800, we have to keep a flame temperature around 920 to 930 degrees centigrade. In the rotary kiln, we have to do the pre-treatment, like we need to homogenize, which is must. Then we need to crush the sample, and we can use the feed size varying from maybe 5 mm to 10 or 15 mm. It seems to work very well for rotary kiln. And the advantage of the rotary kiln is that it is tolerant to high moisture content. We don't need to properly dry the sample before carrying out the calcination using the rotary kiln, and it's versatile, and even if the particle size distribution is different, it seems to work very well. Other than the rotary kiln, at the industrial level, flash calcination technique is also being used to calcine the clays in the large quantities. In this technique, what we do, the pre-processing actually involves first the crushing of the sample. Other than the crushing that we do in the rotary kiln, here we also require the grinding of the sample. And after the grinding of the sample, we do the calcination in the flash calciner. The residence time that we keep normally is in seconds, or maybe even in the deciseconds. And one of the important things here I would like to mention is that we have found that it doesn't actually depend much what type of the technique you are using, whether it's a rotary kiln, whether it's a flash calcination, the pozzolanic reactivity will be the same as long as we are achieving the same degree of dehydroxylation. So about these techniques, whether it's rotary and flash calcination, it will be discussed in detail by Professor Vishnu in another presentation. So now let's talk about the calcined clays. So there are basically two approaches that we can follow to assess the pozzolanic potential of the calcined clays. First is using the advanced characterization techniques like TJ is there, DSC is there, XRD is there, or using the standardized test method. First is the thermogravimetric analysis. The efficiency of the calcination process we can easily check by thermogravimetric analysis. How we can do is that we can perform a TGA experiment even on calcined clay sample to determine what is the amount of the residual mass loss. For the clays, let us assume if we get a mass loss around 4% or 5%, it means those clays are under calcined and there is a raw kaolinite present in the sample. This is because we know that when kaolinite it transforms into metakaolin, it is associated with the mass loss, and if we see a high amount of mass loss in a calcined clay sample, it means that there is significant amount of raw kaolinite which is present, and we have calcined the clay at a lower temperature than what was required to achieve the highest reactivity. Similarly, if you have a properly calcined clay, that will show a residual mass loss roughly around 1 to 1.5%. So that is an indirect indication that we have calcined the clays at an optimum temperature. What we have found in our labs is that for the optimum calcination, we do get a minor residual mass loss. That is actually essential, because if you will get a residual mass loss equal to 0, that indicates indirectly there is an overcalcination. This is because the presence of minor amount of hydroxyl group is actually essential for the stability of the metakaolin. To ensure that it's only metakaolin phase, it's necessary that there should be some amount of hydroxyl groups which are present, roughly 10%. So, indirect indication, if you are getting in a calcined clay sample around 1% of residual mass loss, we have calcined the clays properly. Since kaolinite to metakaolin conversion, it is associated with mass loss, so you can use TGA technique or you can just use the muffin furnace to determine the mass loss. But from metakaolin to crystallization phenomena, that crystallization phenomena, it's not associated with mass loss. So from this technique, you cannot identify whether you have over-calcined the clays or not. So its application is limited only to identify under and properly calcined clays. Then comes the DSC technique, which we have identified in my PhD work that it's a very promising technique, and it can be used to identify not only undercalcination but also overcalcination. The typical DSC curve of the rock clay looks something like this. You can see on the left hand side there are the endothermic peak. The main endothermic peak that is present there, it represents the transformation of metakaolin into the represents the transformation of kaolinite into the metakaolin. While the first exotherm peak that you see here, it represents the conversion of metakaolin into the spindle phase. The spindle is the first recrystallization product that is formed, and if we will increase the temperature further, you will see mullite and cristobalite phases. So, if your clay has just, for example, just kaolinite and only quartz, you will see a main endothermic peak you can see in that figure, and just the one exothermic peak. For example, if your clay has a mixed composition, there's minor amount of 2 to 1 clays. In that case, you will see two endothermic peaks. You can see in this diagram, there is major endothermic peak, which is because of the kyanite, and then you can see a minor endothermic peak that is because of 2 to 1 clay minerals. And you can see here the dehydroxylation phenomena of 2 to 1 clay minerals is takes place at a slightly higher temperature. That is why you first see a kyanolytic endothermic dip which corresponds to kyanite, and then a small endothermic dip which corresponds to 2 to 1 clay mineral. And then you say spinel phase, which is because it has kyanite, so you will see a spinel phase in all the clay samples. So, how to identify and check what's the quality of calcination using the DSC method? You need to first run a DSC experiment on a calcined clay sample. You can get a graph something like that. You can see on the left hand side the red one. Here you are seeing some endothermic dip. So if in a calcined clay sample you see an endothermic dip, it indicates that there is some amount of raw kyanite that is present, because when you are heating that sample in a differential scanning calorimetry experiment, the remaining kyanite is getting transformed into the metaculum. That's the reason you are seeing this endothermic peak. And when you are calcining the clay at an optimum temperature, in the left hand side you can see B1H. Here H represents 800 degree temperature, and for this clay 800 was the optimum calcination temperature. And you see that the endothermic peak is not there, it has disappeared, but you can see a well defined exothermic peak. This exothermic peak is the spindle one. However, there is a possibility that you may heat the sample at a much higher temperature. Let us assume we have heated the temperature at 1000 degrees centigrade. You can see this diagram on the right. There are the two graphs. The one with the yellow line, it's B110, that's B1 clay, which is heated at 1000 degrees centigrade. Here in this graph, you can see that the exothermic peak that has nearly disappeared. So the disappearance of this peak, it indicates that the calcination temperature was high, and this conversion of metaculum into the spinel, it has already occurred during the calcination process. That's the reason when you are heating a sample in the DSC experiment up to 1100 degrees centigrade, you are not getting that peak anymore. So from DSC experiment, you can check whether in your sample it's kyanite present, whether it's the metaculum, and whether it is a spinel. So it can be used both for under-calcination as well as for over-calcination. Then to be sure whether this DSC technique, it works for all the types of kyanolytic clays, and is it feasible even for low-grade or medium-grade clays, we perform this experiment on a large set of clays with different compositions and with different grades of purity of kyanite. One thing we found is that there is not a particular temperature, we cannot have a particular temperature at which a spinel phase will appear. It actually depends. One of the factors that we identified on which the spinel phase, on which this conversion of metaculum into the spinel, it depends on what is the degree of crystallinity of the clays. You can see on the diagram there, the blue one, it represents the clay which has a high degree of crystallinity, and you can see here that the onset temperature of spinel is higher as compared to the clay which has a very high degree of disorder. The one with the red line, you can see there is a difference, and this difference is because of the degree of crystallinity of the clay. We also found that the mineralogical phases and what are the other associated minerals present with the kyanolytic clay, it has an influence on this spinel temperature, and we found that when the clays, for example, there are two clays which have identical kyanite content, they are just the difference of the impurity. The quartz-rich clay give a slightly higher spinel temperature as compared to the iron-rich clay. So for iron-rich clay, we found that the spinel occurs at a slightly lower temperature. Then we also performed this DSC experiment on a large set of clays with different kyanite, and we then looked into the spinel phase, that is determine what's the area, and to determine what's the amount of the energy that is released, and we try to correlate it what's the energy released with the kyanite content, and we got excellent correlation. This excellent correlation, that is between the kyanite content and the energy released, it signifies that this method can be used, and it's a very robust method. It means that DSC method will be able to predict whether the spinel phase has occurred or not, irrespective of the fact what is the composition of the mineral, and it's a suitable test method even for low-grade clays as well as medium or high-grade kyanolytic clays. This means that the associated minerals may have an effect on the temperature at which the spinel phase will occur, but it will not have any influence on the degree of crystallization of the spinel that is bound to happen depending on what is the kyanite content of the clay. So a quick overview, how can you use DSC as a quick test method? First possibility when you are calcining the clays is that under calcination you can check that. You can see if there is an endothermic peak in the DSC experiment, in the DSC curve of a calcined clay sample. It clearly indicates the temperature is low. You need to increase the temperature. For the properly calcined clay, you will not see any endothermic peak. There will be only a well-defined exothermic peak. But some of the cases you might have just exceeded the spindle temperature. Those clays we can say as partially overcalcined clays. You can identify those clays in the DSC experiment. You can see there will be no endothermic peak. But in the exothermic peak, it might be there, but there will be a significant reduction in the peak height or in the area of the spindle peak. So those you can also identify, and if your clay is partially overcalcined, it means that roughly you need to reduce on the calcination temperature by 50 degrees centigrade. Then there's a possibility of overcalcination, which you can quickly identify using the DSC method. And the overcalcined clay will show you a straight curve with no endotherm as well as no exothermic peak when you are performing the experiment up to 11 to 20 degrees centigrade. Other than that, XRD, you must be all using the XRD to identify, to check the quality control. XRD is a very good method, and we can use it to identify easily whether our clays have a kaolinite or not. When there is under calcination, there will be some amount of remaining kaolinite, and because of that, you will get a small peak even in the calcined clay sample. So, which means that it's under calcination. You need to increase the temperature. The properly calcined clays, for those clays, the XRD will not show any kaolinitic peak, and you can see an amorphous hump around 20 degrees centigrade, around 22 theta values, which indicates that the kaolinite has completely transformed into the amorphous metaphyllin phase. But what is interesting is that we found from the clays, that's B110, which was calcined at 1000 degrees, in which the spindle phase was already formed, we could not identify it from the XRD. And we found the same thing, friends, for all the clays that are calcined, in which we can clearly see that the spindle transformation has occurred, it's the spindle phase, but XRD is not able to identify that transformation. So we can say that XRD, from XRD, we cannot identify what is the onset point of overcalcination. It will definitely give you the idea about overcalcination, but when different crystallization products like mullite and cristobalite is formed. So DSC will give you the correct idea about what's the onset point of overcalcination. So other than these test methods, advanced characterization techniques, these have the advantages that they give us a very accurate result, very precise result, and maybe within 1 or 2 hours you get the results. But those techniques have one drawback. You can say that they require a highly skilled operator, not only to perform the test, but also for the analysis, which is not available at all the laboratories. In such case, we can use reactivity test method, which are a lot of standardized test methods are there, which we can use. Based on the duration of the test, we can classify this test method into 3 categories. One is the quick test. There are some test methods which give the results within 24 hours. We can classify them into the quick or the short duration test. There are also medium duration tests, which gives us the result between 1 to 10 days, and there are some long duration tests like strength activity index is there, cement motor compressive strength, which requires 28 days so that we get the idea about the post-aerobic reactivity. So from the reactivity test, let's talk about the light reactivity test. This is a pen-light test for the IS code, IS-1727, and in this test method, we do calcium hydroxide, we take supplementary fluid material, and we extract. We mix it in the proportion of 150 grams of calcium hydroxide, 300 grams of supplementary material multiplied by our structure, which is the ratio of specific gravity of the supplementary material upon the specific gravity of the calcium hydroxide, and we take 25 kilograms of. Then we determine what's the water content. We fix it based on this. Then we determine the water content based on the spread flow test. In which our main target is to achieve a spread flow value between 16.5 to 17.5 ml. We do several trials to obtain this water content. And once we've identified this water content, we can do the casting. We use 50 ml cubes, and these cubes are cured at 2 days at 27 degrees centigrade. And for the next 8 days, they are cured at 50 degrees centigrade. And after we perform the compressive strength, and the posidonic reactivity is related to the compressive strength that we get. So when we perform the line reactivity test on the clays that we suggest for the application of NC3, that's the clays which have a kaolinite content between 40 to 60%. From when we perform the LR test on those set of clays, we are able to identify what is the whether our clays are properly calcined or not. This is because the IS code recommends that there should be a minimum strength of 8 megapascal for the clays to be qualified as ozone. We can identify from the line reactivity test. Also, we can identify what's the optimal calcination temperature. On the first graph, we can see here this clay is approximately 57% of chloride content. We're able to identify that 700 and 800 degrees centigrade seems to look good. We're getting a strength above 8 megapascal, but to achieve our best performance, we need to calcine the clay at 800 degrees centigrade. But if we have a clays which have a very high chloride content, maybe of a nitrogen of approximately 70 or 80%, in that case, we found that when we perform the line reactivity test, we're able to identify whether our clays are properly calcined or not, whether there's a minimum criteria of 8 megapascal. But for those clays, we're not able to identify what's the optimum calcination temperature. In this graph, you can see here the chloride content is approximately 70%. And since in this test we are taking calcium hydroxide and this calcium hydroxide is available in limited quantities, that is the reason for the clay which was calcined at 800 degrees centigrade, calcium hydroxide was less and there was some amount of the material which was not able to react. That's the reason we didn't get it. Optimal calcination temperature for a highly phenolic clay, for a high grade phenolic clay. So this is one of the drawbacks of the line reactivity test. So when we compare the results of line reactivity test with the cement molar compressive strain test, the study was done at Washington Laboratory. There are a couple of papers that they go through, or the IMCC talks about different calcination techniques. And what they found is that the line reactivity test has an excellent, very good correlation with the 90-day compressive strain. The other test I'm going to talk about is modified Chapel test. The modified Chapel test is a heat test because the features of the test is that the to explore are in what this is a standardized test as part of the standard code. In the modified Chapel test, we assess we assess the consumption of the calcium hydroxide in a diluted pH suspension. What we take in this is we take 1 gram of supplementary cementitious material, we take 2 grams of calcium hydroxide, and we place it in a water. We heat it at 90 degrees centigrade for 16 hours, and then after 16 hours we titrate it, and then we determine what's the amount of the unreacted calcium that is present. And then we express our result in terms of this calcium hydroxide at 6 per gram of the test. So when we perform this modified Chapel test on the clay which has a very high chloride content, the same clay that I showed earlier which has a chloride content of 70%, from this we are able to identify what's the optimum calcination temperature, because in this test we are taking almost double the amount of calcium oxide that we take. In this, the clay is the limiting one and the calcium hydroxide is available in the excess. But one thing I would like to point out here is that since this test is performed at 90 degrees centigrade, so we have seen that it can affect the kinetics of the reaction, and we have seen in the results that it is a quartz which is completely crystallized. We have seen that it just shows some amount of the organic reactivity because of the high temperature that we are using. Since in the modified Chapel test, we are measuring what's the consumption of the calcium oxide. So this consumption of these calcium ions, it is definitely related to the chemical reactivity, but there can also be another phenomena, that is the absorption. We have identified maybe for other supplementary materials, the absorption phenomena is really less. So whatever we are making is, we can relate it more or less directly to this chemical reactivity. But for the clays, we have found that there is a very high absorption, and in the modified Chapel test, actually we are making both the things, the absorption as well as the reaction. And we have also found that for the clays, for example, we perform the modified Chapel test on the clay which is calcined at 400 degrees centigrade. It showed us a very high modified Chapel test value, and then we did the graph and resistance results, so we got a very low strength. So there was like a difference, and we found that there is a high absorption at a low calcination temperature as compared to the clays which are calcined at a high temperature. So this means that the difference that's between the modified Chapel test reading from one temperature to another temperature, it cannot actually represent what's the increase in the chemical reactivity, because we are measuring absorption and reactivity. Then another test that's commonly used is the RT test. RT test is a standardized test method as per ASTM C1897. In this test method, we take supplementary cementitious material, we take calcium hydroxide, we take calcium carbonate, potassium hydroxide, and potassium sulfate. We take these things to mitigate the structural environment in the cement solution. There are two methods that we can use in the RT test. First one is the isothermal velocity. In this test, we measure what's the heat of hydration of the base over the time. While in the bound water test, what we measure is what is the bound. In this test, we measure what's the mass loss because of the bound water and we measure directly to the chemical reactivity. Both these methods can be used. It depends upon the availability of the equipment. And this test is performed at 40 degrees Celsius. There have been a lot of studies which have been done on the RC test using different types of SCMs and different types of clays, and they have found that there is a good correlation of RC test with the 7 and 20 days from persistent results. So when we are measuring the heat of hydration, we have to be careful that we are actually measuring the heat of reactions that is involved from a particular sample. What I mean is that there are different types of solar machines are available in the market and they have a different design and it can actually affect our results. Because, for example, actually the calorimetric design should be such that each calorimetric cell is separated so that we measure actually the reaction of each sample cell. So that there is no crossover also, and in our laboratory we are using the CAL matrix type isotel, and we found that in this test method we are not getting any noise because of the other isotel compartment. So we would recommend that maybe we should also add calorimetric if you are thinking of purchasing the isotel, and we have been using in our lab from maybe 15 years and it's working perfectly. We have no issues, and the person here at the design. He's the one who looks at the calorimetrics and suggests that you should buy it. Maybe you will get some discount also. Yes. So now let's talk about another test method. This is the Reactivity test. This test method is standardized as per the British Standard Code. In this test method, we take the pozzolanic cement and we mix it with the water and then we keep it at 40 degrees centigrade for 28 days. And then we measure what is the concentration of the calcium and the hydroxyl ions. This is a qualitative type of the test. We can identify from this test whether our material is reactive or not. If the reading of the sample will be below this curve, it indicates that it's a reactive sample. If it will be above, it indicates that it is non-reactive. It is this method since we are using the cement, so the results will be highly influenced by what is the physical and what other characteristics of the cement. In our laboratory, we also use electrical conductivity, and I'm using the PhD work also. We are basically the main idea of the electrical conductivity test is that when we take up, for example, a calcium hydroxide solution, we place the clay in it, and when we place the clay in it, there will be the chemical reaction, and because of those chemical reactions, there will be the decrease in the conductivity. So we are trying to measure this, what's the change in the conductivity, and trying to correlate it with the pozzolanic reactivity. We performed this test for a wide range of clays with calcium at different temperatures. We found that the electrical conductivity test is able to differentiate whether our clays are properly calcined or they are under-calcined within 120 minutes. It works both for high-grade calorimetric clays or low-grade calorimetric clays. Then we tried with the different compositions. We found that even when light is present, it works very good. We are able to distinguish over-calcined and under-calcined clays. But for the clay, which had a very high iron content, we were not able to differentiate what's properly calcined or over-calcined. So far, I talked about the standardized test method. Then our main objective was to identify whether we will be able to identify the quick test method which can be used at an industrial level. One of the attempts we thought initially that it will work was the water demand. We looked into the literature and tried to identify what are the potential test methods that we can use to check what's the water demand. And our hypothesis was that water demand will give us a rough idea about the quality of the calcination. We started first with the Punke method. In this method, it defines the water content as what's the minimum water which is required so that the material will be the transition from the granular to the suspension state. We also tried the classical method, the same test method that we use for to determine the normal consistency. We follow the same protocol. We use also the spread flow test to check what's the water demand, and we didn't find the result that what we actually expected. We found that the water demand doesn't change much during the calcination period, so we were not able to distinguish from water demand test whether it's under-calcined or properly calcined, because water demand actually depends on so many factors, so it was difficult to identify whether it has a direct correlation with the degree of calcination, or we were not able to identify this. So then we didn't move further with this test method. Then we were able to identify the two test methods. So the two test methods that we suggest are suitable for the industrial application. The advantage of these two test methods is that they are very simple, it doesn't require any sophisticated equipment, and it uses the results within 15 to 20 minutes. It is a combination of methylene blue and density test. From the methylene blue, we can check whether our clays are under calcined. I mean, we can check what is the degree of conversion of chloride into the metal. We can check it from methylene blue, which is a very simple test. Then the conversion process of metactive into the spinel phase, we can check it from the density. So by combining these two test methods, we can check whether our clays are under calcined, properly calcined, and over calcined. If you want to know more about this test method, we have a detailed discussion later. Then coming to the final topic, that's what are the factors which affect the pozzolanic reactivity. The main factors that we can say is the calcination temperature, its clay mineral, what are the other minerals that are present, degree of crystallinity, and the specific surface area. Calcination temperature, we have talked too much in this presentation. Now let's talk about other clay minerals. In my PhD work, I looked into the chlorinated clays, but other than that, I also explored the smectite clay, and we found that the smectite clay can also show a very high pozzolanic reactivity. You can see this graph. If you look at talk about the composition, in this clay there is zero chloride content, but still you are getting a very high line reactivity value of around 11. So it's just not the chloride that can be used as supplementary cementitious material. There are other clay minerals that we should investigate, and they may also have a possibility of using it as a supplementary cementitious material. So far we have identified that smectite is one of such clay minerals which can be used as a potential supplementary cementitious material, and in fact it has a very high pozzolanic reactivity. The one thing we have to be careful with this, for example, with this type of clay, what we identified was the calcination temperature. It was very sensitive to the calcination temperature. We found a 900 degree, for example, in this type of smectite clay, it was the optimum temperature. Had we calcined this clay just at 800 degrees, we would have realized that maybe it's not working. So the calcination temperature is very crucial while we want to achieve a high pozzolanic reactivity. We need to identify. Talking about the other associated minerals which can have an influence on the pozzolanic reactivity, we found that the chlorinated clays which are rich in iron, they basically show a higher reactivity, and that too they show a higher reactivity at a very low calcination temperature. So iron-rich clay reduces the optimum calcination temperature. We need to calcine the clays at a slightly lower temperature as compared to the clays which we have on the quartz. Again, we also found for the clays, for example, for the chlorinated clays which have some amount of one clay mineral, it has a positive impact. We found that if we calcine the clays at a slightly higher temperature, not close to the crystallization, somewhere between the optimum calcination temperature of the chlorinates, we found that they are able to hydroxylate to one clay minerals also, and they are able to achieve a higher strength. Talking about the crystallinity, we have found that crystallinity is also another factor which affects the pozzolanic reactivity. We can measure this crystallinity using XRD or by some FTI technique. There are a couple of indexes that we can use to check whether is a high degree of order or a high degree of disorder. We found that the degree of order or disorder, it depends on the composition, and we found that the iron-rich clays are highly disordered, and maybe this is one of the reasons that we are getting a very high reactivity, even at the lower calcination temperatures. Then we determined the specific surface area using the BG method, and we found for a different chlorinated clays which had a different composition, we found that the specific surface area was varying a lot. Even for the same grade of chlorine, there was a huge difference in the specific surface area. And then we found that there's a very good correlation actually between the specific surface area and the iron content. Higher iron content, we're getting a higher specific surface area of the rock clay. And then when we calcined the clays, we got a similar thing. We got that the iron-rich clays have maybe the double specific surface area as compared to the quartz-rich clay even after the calcination, which means that maybe for the iron-rich clay, we need to increase the richer dosage, and we have to be careful with this thing, and we should take this point into consideration. And if I talk about the morphology, we got a similar result as we see in the specific surface area. The clay which had a high degree of crystallinity, we saw properly layered structure, while for the clay which were really rich in iron, we found even in the semi-emergent clay, a very small clay particles were present, which confirms the hypothesis about the reach results. So that's all from my side. Thank you.